Hello everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm going to deal with the course Computational Aerodynamics. So in today's class, we'll be seeing what is forward, backward differences in space. So which is like you have forward in time, central in space, forward in time, forward in space, and forward in time, backward in space. Okay, so let's see actually what is computational fluid dynamics. So as we discussed, so the flow approach can be in three ways. So one can be pure experimental method, other can be pure theoretical method, and other can be computational fluid dynamics too. So initially during 13th, like 15, 16, 17th centuries, so people had actually performed this flow experiment flow analysis using like experimental setups, and it is being calculated using theoretical knowledge. But the modern tools has brought like CFD approach, where the governing equations are solved numerically to get the fluid flow, uh, or to get the flow properties of the fluid flow at various fluid flow problems. So first, the thing is that so we have different sets of fluid flow problems. So whatever the fluid flow problem that we have, so we use basic equations, governing equations, which is first continuity, which is conservation of mass. So mass conservation. Next, momentum. Third one is like energy. Okay. So these three are very important to solve any fluid flow problem. So first, if the flow speed is less than, let's say, 105 meter per second, so the flow is said to be an incompressible flow or a low speed flow. So in the low speed flow, so the conservation of mass and conservation of momentum, so these two would be sufficient. Okay, so at low speed, so these equations are sufficient to solve fluid flow problem. So we have to calculate the properties such as pressure, u velocity, v velocity, w velocity. So this is what we have at a low speed flow. So where we assume that the flow is incompressible. So for the incompressible flow, the density is assumed to be constant. So therefore we have pressure, u velocity, v velocity, w velocity. So therefore mass conservation, momentum conservations would will be enough to calculate the flow problem. So if we see the continuity equation, so dou rho by dou t plus del dot rho v equal to 0. So this is the generic equation of the continuity. So this continuity equation will tell us whether the flow is incompressible or compressible. Okay, and it can say whether the flow is steady or unsteady, whether the flow is uniform or non-uniform. So these things can be said from the continuity equation. So this continuity equation cannot give any information regarding the flow, whether it is inviscid or let's say if the pressure terms, so whatever it is, so here we can say whether the flow is incompressible or compressible, and steady or unsteady, and uniform or non-uniform. So if the flow is incompressible, so the density term here gets cancelled. Then we whatever the second term is there, which is space derivative term, so we have del dot v is equal to 0. Okay, so this is called the divergence. Okay, so this is an incompressible continuity equation. Fine. So if the unsteady steady continuity equation, if we need to write, so what happens? So rho del dot rho v equal to 0. So which is steady continuity equation where the flow is compressible. Okay, so if the flow is incompressible and steady, so then this equation will hold. Fine. So basically the divergence will actually be used for the incompressible flow medium. Fine. So coming to the momentum equation, so this momentum equation is basically starting or originating from the equation which is F is equal to m into a. So force is equal to mass into acceleration. So force is nothing but a rate of change of movement. So here you can see, so dp by dt, so which is nothing but f. So f external, so which is equal to d by dt of m into v. So this is what we have. Fine. So basically the force which is acting on the fluid particle is majorly due to rate of change of momentum. So the force acting on the fluid particle or any system which is moving with the flow will be categorized in two ways. So let's see what are those two ways. So F is of two. One is body force, other one is surface force. Okay. So the body force is majorly involving with gravitation. So basically gravitational force. So basically here the gravitational force is majorly involved for the body force. The surface force is majorly due to pressure and here viscous. So basically the pressure and viscous force. So the momentum equation will give us the information regarding the pressure gradient and the shear gradient, and then after you will know the local acceleration, convective acceleration, and the body force term. So for a low speed flow, the continuity equation and the momentum equation alone would be sufficient to solve the flow properties and get the values. But when the flow speed crosses, let's say greater than 105 or 110, let's say, when the flow is said to be compressible, then we no longer assume that the density is constant. We should use the density term in continuity equation and momentum equation, and therefore when the flow is getting compressed, the temperature effects are very predominant, so energy equation has to be used. So therefore all the three equations has to be used to get the flow properties for different fluid flow problems. So these equations are already been put forward in theoretical methods, and people used to calculate in analytical way. But whatever these equations that we have to solve any fluid flow problem, now CFD is using those equations and solving those equations with appropriate numerical techniques. So we'll be seeing what are those appropriate numerical techniques, whether those techniques are stable or consistent, whether the numerical scheme is able to converge, and whether the error associated with the numerical scheme is within the limits or not. So we need to see these many things. Okay. So having said these things, so let's go for the uh, FTFS, FTBS, FTCS schemes. So first of all, like where do we use this FTCS? Where do we use this FTFS? Where do we use this FTBS? We will see. Actually, these things are implemented in our governing equations. So let's say, so we have d rho by dt in the continuity equation plus, so let's say we have rho by dou x of rho u plus dou by of rho p plus by dou z of rho w, which is equal to 0. So this is the full form or the full-fledged continuity equation. So if we assume the flow is said to be incompressible, what happens? So this term is 0, okay, and the density terms will not be there. Okay, so here you can see dou u by dou x, dou v by dou y, dou w by dou z is equal to 0. So this is what we have. So but if we, so here you can see ft, so which is nothing but forward in time. Okay, so we need to see what is the approach for the unsteady equations. Fine. So now we have to use density terms. Then let's say if we see for the momentum equation, so we have the pressure gradient terms, which is on the right hand side. On the left hand side, so you have, let's say, u into dou u by dou x plus v into dou u by dou y. So this is what we have. Okay, so these terms, so whatever these terms we have, so let's say, so these are space derivatives. Okay, so if we consider the first one, the time derivative, so these terms are replaced using these ftcs, ftfs and ftbs scheme. Okay, so let us consider an unsteady transient heat equation, sorry, an unsteady one-dimensional heat equation. Let's say. So dou t by dou t plus alpha dou square t by dou x square equal to 0. So unsteady, let's say the diffusion equation. So this is what we have. So this equation so can be solved in the three ways. So one is FTCS, other one is FTFS and FTBS. So basically these approaches are finite difference schemes. So what is the finite difference schemes? So basically we solve the partial differential equations using the appropriate numerical approach at the grid points. Okay, so basically these are grid points. So we'll be doing the discretization at the particular grid point. So once we do the discretization at the particular grid point, we'll be getting the algebraic equations. We collect those things and invert the matrix. So this is what we have. So now, so let's implement these schemes for the particular problem, which for the particular equation which is shown here, and let us use this grid, sample grid. So already we discussed, so let us refresh it again. So for the time, we will use the superscript index, which is n. Okay, so for the space, so we'll be using, let's say, ix. The index notation is I. For the y, the index notation is j. For the z, the index notation is k. Okay, so these are the different index notations. So when it is set to have a forward in space, then you have I plus 1 and I terms. So if it is along x we are talking, so the I plus 1 and I terms will involve. So if it is backward, I and I minus 1. If it is central, it is between I minus 1 and I plus 1. So these are the terms which are involved. So first thing, so which is forward in time and central in space. So for the forward in time, so we have a time derivative term here, which is dou t by dou t. So here you can see. Okay. So here you can see how it is written. So basically this is like Euler. So it's a first order difference. So you can see. So here T of I. So T of I in the sense, capital T of I in the sense, the temperature at the ith grid point, at this grid point, at next time level. So if we consider n as initial time level, so n plus 1 is the next time level. So we need to know the value at this particular grid point at the next time level. So we will be knowing what is the temperature at the initial time level. Okay, so if we want to know the temperature at the next time level, so we need to see what are the factors that are involved. Okay, fine. So now we had seen ft, forward in time. So let's see for the central in space. Okay. Okay, so this is the formulation. This is the formulation for the forward in time, central in space. So here you can see the central in space. Uh, so basically here, this is the second order derivative. Okay, so for the first order derivative, like we have I and I plus 1 and I minus 1 terms. Okay, so which is like dou t by dou x. So let's see for the other example also. But meanwhile, so this is the second order derivative where we can see the central in space formulation. Now, if you observe clearly this equation, so there are one unknown, like there is one unknown which is t of I to the power of n plus 1. So this is an unknown value. So remaining all, we know these values. These are the known values. Okay. So initially, so we'll be knowing what is the value of the temperature at the all particular grid points. Let's say at I plus 1, I minus 1. So these are the initial values. So initialization. So basically when you give initialization to the domain, so you'll be knowing the values of the grid point at each and every corner and each and every node. Okay. So after the initialization, when you start simulation with appropriate boundary condition, so we need to see the updated values at those grid points at different time levels. Okay, so this is the value at time level n. So at time level n plus 1, so this would be another set of values with the grid points. Okay, so basically what we do, so we have this left hand side, so which is a unknown value. So here we have this all known values. So we will rearrange and get the value of temperature at n plus 1 time level. Okay, so this is how we do for forward in time, central in space scheme. Okay, so let's see for forward in time and forward in space. Let's see a 1D wave equation, which is dou u by dou t plus a into dou u by dou x, so which is equal to 0. So this is a 1D wave equation. So where you will be seeing, so this FTFS, like FTCS, FTFS, FTBS. Okay, so let's see this one. So now what we have, so already we discussed for forward in time. So what we do, so we have u to the power of n plus 1 at I level minus u power n divided by delta t. So which is nothing but forward in space plus, sorry, forward in time. This is forward in time. So next a into dou u by dou x. So this is central in space, which is u of I plus 1 minus u of I minus 1 divided by delta x equal to 0. Okay. So here you can see basically this is a first order. So for the first order scheme, so you can see first order derivative. So here you can see we have I plus 1 and I minus 1 terms. Okay. And here you can see for the time we have n plus 1 and n. So this is only so forward in time. Okay, so you have central in time also, but now we are discussing forward in time, central in space. So that is called CTCS, central in time, central in space. Next you have central in time, forward in space. So these things, so also you can see, but so we propose so many numerical schemes, but we need to see which one would be efficient and which one is stable and which one is consistent and which one will converge. Okay, so there is nothing to like to write, so we can write easily by saying it is CTCS, CTFS, these things. But when we write these things to a particular equation, so we need to see how it is reacting with time. So let's say I am saying with stability criteria and with errors and consistency. So these things we need to see. If a numerical scheme is not consistent, not stable, not convergent, then it is useless of using to a particular fluid flow problem. Okay, so therefore once, so we have numerical scheme, like numerous numerical schemes. So we need to first evaluate the stability, so which we'll be discussing in the future classes, and convergence, and then after consistency. So these things we'll evaluate. Then you can use that particular numerical scheme to solve the particular governing equations for a given particular fluid flow problem. Okay, so this is one sort of approach where you have FTCS. So next, next we have FTFS. So FTFS, so basically it says, so FTFS basically it says, so foreign times, which is u of n plus 1 minus u of n divided by delta t, so which is foreign times same, but you have foreign in space a into, so u of I plus 1 to the power of n minus u of I n divided by delta x is equal to 0. So this is what we have. Okay. So basically what is the unknown value we have here? U to the power of n plus 1 at I level. So these all are remaining all are unknowns. Sorry, these are all known values. Only u to the power of I to the power of n plus 1 is the unknown value. So this is one sort of technique to calculate. So there are numerical techniques where we can solve the problem. So in this approach, we'll be seeing how do we get the value of the velocity at the particular grid point at next time level. So this is FTFS. So next for the FTBS, so what we have is like u of I to the power of n minus u of I minus 1 to the power of n divided by delta x is equal to 0. So this is what we have for FTBS. Okay, so these three, so FTCS, FTFS, FTBS, so they solve the numerical procedure in different manner, but whatever the manner they solve, so we should be able to get the values of fluid properties at different problems in a stable manner, and the solution should converge, and the scheme should be consistent. So now in the further classes we'll be seeing so which scheme is numerically stable. So the stability is very important criteria for a numerical simulation. So if the numerical scheme is not still stable, then it's waste of using. So there is a testing facility which is called von Neumann stability. So the von Neumann criteria will give you so in which way, so like the scheme can be stable. So what should be the like damping factors, and how we can actually do some changes for the scheme to get the stability, and what are the criterias to use in the simulation to get a stable simulation. So these things will be seen. So we'll be evaluating so FTFS, FTCS, FTBS. Out of these three, like let's say which numerical scheme would be like conditionally stable, unconditionally stable. Okay, so these things we'll be seeing in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.